Hello, math people. Welcome. We are looking here at limits involving infinity, and what I hope to do is draw the very obvious and strong connection between limits involving infinity and the horizontal asymptote. So let's look at a graph of some function here. Let's think about the graph y equals 1 over x, and we know what that looks like. It's a rational function, and the horizontal asymptote, which is something that you studied in pre-cal of this function, is y equals 0. But what is the horizontal asymptote really investigating? The horizontal asymptote is telling us, it's saying, what does y approach as x approaches infinity? So the horizontal asymptote is really, and you were doing this in pre-cal, it's just the limit as x approaches infinity of my function. And this equals some value, and we'll call that value L. Okay, well, before we proceed with some definition issues around limits involving infinity, let me just remind us or remind you about the rules that you should know in just because you know them for horizontal asymptotes. There are three cases for horizontal asymptotes. Case number one, and these are all dealing with rational equations, but the power in the numerator is greater than the power in the denominator. Here's an example. Or the denominator power is greater than the numerator. Here's the example of that. Or the powers are the same. Okay. Well, if the power is greater in the numerator, then there is no horizontal asymptote. And we say the limit, let me write that a little bit better. In this case, the limit does not exist because we're not approaching a fixed number. When the power is greater in the denominator here, it's a 7. The horizontal asymptote is y equals 0. And so the limit as x approaches infinity of my function equals 0. And the last rule that you should be familiar with is if the powers are the same. And if they are the same, which they are here, then we look at the coefficients. So our horizontal asymptote is y equals 3/2. And as a limit, we say the limit as x approaches infinity of f of x equals 3/2. So let's actually go ahead and take a stab at defining limit. So the limit limit as x approaches infinity of f of x equals L exists. So there's cases where it doesn't exist. if and only if, as x approaches infinity, y approaches a finite number, so a fixed number, a finite number, and that finite number is L. So an example of where a limit doesn't exist, let's think about this. The limit as x approaches infinity of x, well, what does that graph look like? It just goes on and on and on and on. So as x approaches infinity, my y value is also going to approach infinity. So it doesn't uh, approach some fixed number. So we say that this does not exist because it doesn't meet the qualifications, because it does not approach a finite number. Okay, so some theory before we go ahead and prove those rules that we were using in pre-cal. That's the real crux of today's lesson, is to prove why those horizontal asymptotes rules, why they existed. And it all hinges on this idea of 1 divided by a big number. Well, we know that 1 divided by a big number, and by big I mean huge, I mean infinity. 1 divided by a huge number gets close to 0. So therefore, the limit as x approaches infinity of 1 over x to the n, where n is any positive number, well, as x gets close to infinity, this is going to get huge, and we know that 1 over a huge number, well, approaches 0. So the, in this example, this bottom example, I want to show why, as x approaches infinity, this approaches 2/3. And so we're gonna prove on the next page how to use limits and calculus to prove this idea of horizontal asymptotes. Okay, this is a fun little proof. The idea is choose the highest degree, not choose, but find the highest degree. And the highest degree in this problem is x to the 4th. And we're going to divide everything by the highest degree. Every term. So we get 2x to the 4th over x to the 4th plus 3x squared over x to the 4th. And I'm going to go ahead and fill this out. And when you come back, you'll see it all done. So by dividing every term by x to the 4th, what will always happen is that we're going to get a system or a situation rather where we will force there to be, let me go back a page, we'll force there to be the situation where we have something being divided by a huge number. We're going to force this sort of situation right there. So how? Well, let's, oops. So we divided everything by x to the 4th. Now if we simplify that, we get the limit as x approaches infinity, and people have the tendency to not write this. Always make sure to write it. And we get, well, x to the 4th over x to the 4th is just 2 plus 3 over x squared plus 1 over x to the 4th over 3 plus 2 over x squared minus 8 over x to the 4th. All right, cool. So as x gets close to infinity, as x approaches infinity, we have 3 divided by a huge number. That's going to go to 0. 1 divided by a huge number, 0. 2 divided by a huge number, 0. 0. And what we're left with is this 2 over 3. Those are my leading coefficients. And that's exactly why, that's where that rule comes from. So we get that this equals 2/3. So what I want you to do is use that proper limit algebra to prove that the limit as x approaches infinity of x to the 4th plus 3x squared over 5x to the 7th plus 2, this equals 0. So pause the video, do some division. I would say x to the 7th might be a good dividing term. Do some division and prove that this limit is 0. Okay, here we go, math people. So we got the limit x approaches infinity, dividing by x to the 7th, because that's the highest power. We get x to the 4th over x to the 7th plus 3x squared over x to the 7th. Now, you may be asking, why do we need to do this if we already know those rules from pre-calculus? Again, the purpose of today's video really is just to make clear those ideas and to show why those rules are the way that they are. You could just say, well, when you're asked to do these problems on your homework and it says, find this limit, you could just say, well, the power is greater in the denominator than the numerator, so therefore it's 0. But here we're proving why. So when we simplify this, doing a little bit of simplifying, we get this is the limit as x approaches infinity of 1 over x cubed, that's this, plus 3 over x to the fifth over 5 plus 2 over x to the seventh. And as x gets huge, as it approaches infinity, this, and this will all go to 0. And so what we're left with is 0 over 5, which equals 0. So that's it. Hope this made some sense.